The desk test checks if an algorithm has the characteristics that are needed. Usually, we start with designing an algorithm, like I did here for the function power. And when we have designed the algorithm by describing its behavior, then we can test the algorithm by using the desk test. For the desk test, we need a chart like this one on the right side. And in this chart, the single values are going to be written. And now I'm going to look at the power function, which is simply an exponential function which uses a given exponent to a specific basis to calculate the power. And now I'm going to test it. As an example, for the basis, I'm going to use the number 2 and 3 as an exponent. Mathematically, this is 2 raised to the power of 3, so 2 times 2 times 2. And the result should be 8. So, in this algorithm, we have the lines 1, 2, 3, and 4. This is the body of the function. And we address the function power using a 2 as value for b and with 3 as the value of e. And now we can start. We begin in the first line and enter the values of the different variables. And the variables are b, e, and p. After finishing one line, and at the beginning we are in line number 1, b has a value of 2, e has a value of 3, and p has a value of 1, because it received the value 1 in here. We continue with the next line. And in there we can find the head of the loop, which contains the variable I, which we have to insert in here. I'm going to extend the chart and write another I in there. In line number 1, the variable I was not known yet. That's why I put a dash in there. So at the end of line number 2, b is still 2, e is still 3, and p is still 1. And I has the value of 0. And we continue with line number 3. At the end of line number 3, b is still 2 and e is still 3. And p is now calculated by using p, which is 1 at the moment, times b, which is 2. So the result for p is 2. I is still 0. Now we are at the end of the for loop, which has its head up here. And now we restart at line number 2. At the end of a for loop, we always return to the head. And now we check if the condition is still true, which, if it is true, leads to the restart of the for loop. Now we are back in line number 2. B is still 2, E is still 3, P hasn't changed anymore and is still 2, but I has changed. Now it is 1, because I has been increased by 1 at the end of the body. So, now we are back inside the body. And now we are in line number 3. B is 2, E is 3, and P is calculated by using P from the line prior to this line times the current value of B, which results in 4. I is 1. And now we jump back to the head of the for loop because we have reached the end. And now we are back in line number 2. B is still 2, E is still 3, P is still 4, and I has changed to 2. And because 2 is still smaller than E, which was the condition of this for loop, we re-enter the body of the for loop. And at the end of line number 3, we still have B as 2 and E as 3. P is again calculated with P from the prior row times the current B. And 2 times 4 is 8. And I is 2. Now we have returned to the end of the for loop, which means we return to the body. And now we are back in line number 2. B is 2, E is 3, P is 8, and I has changed to 3. And now the variable I doesn't fulfill the condition for it being smaller than E. And that's why the body of the for loop isn't executed anymore. And I skip the body and return straight to line number 4. And in line 4, we have B with a value of 2, E with a value of 3, P with a value of 8, and I doesn't exist anymore. And in here it is said that the value of P will now be returned. And if we take a look at the value of P, we see that it is 8. And that is what's going to be returned, and we can write power of 2, 3 equals 8. Which is correct as far as we know. And now, by using the desk test, I could prove that the algorithm, which I have written here as a pseudocode, works at least for the basis 2 and the exponent 3. Which doesn't mean that it works for every other case as well, but it means that it works at least for this case, and that gives us a bit of certainty about the functionality of the algorithm.